Okay, good afternoon, everyone. So we're very happy to have Martina Rovelli from the University of Massachusetts at Amherst, who is going to tell us about n-Complicial sets as a model for infinity n categories. Martina, please go ahead.
Thanks a lot for the introduction and for the invitation. Maybe the plan for today is the following. We may know that the language of infinity n categories is used and maybe even needed to phrase certain aspects of topological quantum field theories, in particularly the extended ones. And we may have an idea of what we expect from the behavior of an infinity n category, but if we ever try to work with them and write down a mathematical definition, probably very soon we would realize that there are a lot of subtleties and that it's hard to work with it. And in fact, there are many mathematical responses to the question of what is an infinity n category. And essentially what I'm doing today is I'm exploring one of these possible responses. Namely, I'm gonna discuss with you a little bit a specific implementation of the definition of an infinity n category, which is the one of n-Complicial sets. I'm going to start by maybe remind ourselves a little bit of what is the type of structure that we expect, and then I will dive into a specific proposed definition. And I think I'm quite flexible, so feel free to stop me at any point if you have any questions. So you see I have a table over here. On the left, I'm gonna fill in the type of structure that we expect in general, but instead of giving that one directly, let's first deal with the right column where we want to insert things that come from an example. And one of the main higher categories that people would consider is some flavor of a higher category of cobordisms. So what do we find in there that we hope to incorporate in whichever structure we're trying to define? Maybe at the first level, at the zeroth level, what we see there are something like closed zero manifolds. And you go on, you're like, okay, once I have two zero manifolds, I want to have them interact with each other. What do I do? Well, I could consider maybe cobordisms between them. So maybe let's just say one cobordisms. And it's convenient to actually allow boundaries. And now to go from here to the next step, you can probably imagine that you're just jumping one level up. So you could have now two cobordisms with corners. So let's draw some of the typical pictures that one would see at this point. An object is a closed zero manifold. So for instance, this set with 2 points would be one zero-dimensional morphism in the higher structure that I'm trying to define. And I could look at what are the cobordisms from this object to itself. Here are two possible cobordisms that I could draw. There is this one, and there is also maybe a more interesting one that connects the dots differently. And now I could imagine to further try and connect these two one-dimensional cobordisms via a two-dimensional type of thing. So let's try and draw it. Can you see this color actually, or should I pick another one? I'm gonna go black. So maybe this is one of the two that I drew. This is the other one, and you could imagine to connect the two with some kind of surface that looks like this. So what is the role played by the information introduced so far? well, I already kind of used these out loud. I'm thinking that the closed zero manifolds are the zero morphisms that usually we just refer to as objects. And the one cobordisms would be the one morphisms. They go between objects, and the two cobordisms would be the two morphisms. Okay, I could envision to just continue this way all the way up to infinity. But there is a parameter here that is kind of fixed throughout the talk. It's this n over here. So we expect that at n something critical should happen. And indeed, we use this parameter to specify that even though we were going to allow morphisms in every dimension, after level n, we expect that all these morphisms are going to be invertible in some sense. So I could continue in this way all the way until n morphisms. So this would correspond to n cobordisms. And this is the same n that is in the title. But then I expect that after level n, I will only consider some kind of n+1, n+2, n+3 morphisms that are invertible in some sense. So in here, I'm going to record that I expect, oops, some invertible n+1 morphisms and some invertible n+2 morphisms, and so on. In the practical case side, usually what you would put at this point is something like diffeomorphisms between the cobordisms, and I would expect these to preserve like boundaries and corners appropriately. And I could also go up and maybe have something like isotopies and so on. Okay, so here we lay down kind of the expectation that we're going to have morphisms in every dimension, invertible in some sense after level n. But that's not it, because if we think about it, we have more. We also have some kind of composition laws that we really would like to encode and incorporate in the type of structure that we're trying to define. So on the abstract side, I would say that we also have a composition of morphisms along morphisms of a lower dimension. So maybe composition, maybe I just say along morphisms of lower dimension. So in the practical case, this can manifest itself in two ways. If I'm still in the range of like before the critical point, so somewhere here, I could imagine that I take two cobordisms that would like to be glued, and I could glue them together. Instead, if I am in this range, here the morphisms are functions of some kind, and so I can really compose them in the sense of functions. So I would have the fact that I can glue cobordisms or compose diffeomorphisms, and so on. So everything looks good, and it would be very tempting to just now define an infinity n category as something that has morphisms in every dimension and that compose appropriately. Probably we could imagine a nice list of axioms that we'd like to be satisfied and call it a day. So one could do that. The problem is that the naive list of axioms that we would like to write down would fail to actually incorporate the examples that we care about. For instance, we would really like to say that this composition of morphisms that we claimed exist is associative and unital. But then if we try to be diligent and sit down and try to verify the associativity of this composition, we would find ourselves facing the following situation. We take 3 cobordisms, say some sigma, sigma prime, and sigma second, that are trying to be composed with each other. So maybe we need to have one of the boundary components of sigma to agree with one of the boundary components of sigma prime, and same with the second pair. And I could glue the first 2, and then the result with the other one, or I could choose a different bracketing to kind of produce a competing output. So I'm rewriting the same thing, just with a different bracketing. And once again, maybe it's tempting to say that these 2 things are equal, but they are not. This is only 2 manifolds that are canonically diffeomorphic. So maybe it's a fancier manifestation of the fact that just gluing things together, as we learn in algebraic topology, is not associative on the nodes, like the lengths are messed up. And the fact that I have a canonical way of comparing the 2 sides doesn't mean that I'm allowed to write an equal in there. So this is a diffeomorphism. Okay, so then I cannot be as optimistic as I had hoped. I cannot say that this composition has to be associative. And there's a similar issue with unitality, which would correspond to gluing kind of a cylinder over one of the boundary components of a cobordism. So I have to be a bit more flexible, and I have to allow that associativity and unitality of this composition should hold weakly in a certain sense. And this is where all the trouble begins, because trying to formalize precisely the degree of weakness that we are after is a giant pain. So what does weakly mean? And if we are inspired by the specific example that we've been looking at, maybe we expect weakly to mean something like up to a higher invertible morphism. And I could try to kind of save the definition and still take some sort of axiomatic approach, but I would realize that there's a sort of circularity going on. Let's see why. Questions so far before I leave the table?
Any questions? I think all is good. Yeah, let's proceed.
Cool. Okay, so here's the issue. This idea is kind of circular. So I can still have it as an expectation for whichever notion of infinity n category I'm going to pick, but I cannot take it as a well-formed definition. So why is it circular? One way of kind of highlighting this circularity is to compare 2 things that featured in the wannabe definition. One was the notion of composition, and one was the notion of invertible morphism. And I could ask you, which of these 2 notions is more elementary? And you can't really answer this, because composition is used to define when a morphism is invertible, like invertible with respect to what? With respect to composition. So in this sense, composition will be more elementary than invertible morphism, used to define. But the latest issue that we highlighted also showed that I need to know what an invertible morphism is to express the axioms for composition. So invertible morphism is a concept used to state the axioms for compositions. So this is where I need to take a step back. And as I said, I can still keep the table that I explained as kind of a shadow, but I need to enhance this concept in a way that it's well-formed and that is going to reflect my expectation. And this led to the idea that there are in fact many models, many mathematical ideas to implement my expectation. So here is a non-comprehensive list. One possibility is to take Verity's approach and to study n-Complicial sets as a model for infinity n categories. And this is what we will be talking about today. But there are other ways, and you could imagine giving another talk where you explore another model instead. So Barwick did the n-fold complete single spaces. So these are based on multi-simplicial spaces. Resk did complete Siegel theta n spaces. Ara did n quasi-categories. And recently there was a model developed based on cubical sets due by these authors in different combinations. There's Doherty, Kapulkin, Maehara, and it's based on comical sets. Okay, so this is not, I would say that this is not a competition. I have used different models for different purposes. And the truth is that different models have different advantages and disadvantages. So it's more like, I see it as it's good to understand as many models as possible, understand how they compare to each other, and draw from the better behaved one depending on what is your goal of the day. Okay, so that's the end of the kind of introduction, and I'm ready to dive into the definition of an n-Complicial set, and that's my main goal for the day. Okay, so here are some definitions. This part is going to look more mathematical, and I'm going to start by recalling something that we may be familiar with, and is the notion of a n-complex. And I'm doing that because the definition of an n-Complicial set is the closest definition of an infinity n category that resembles n-complexes and quasi-categories, which are more like classical and traditional objects in simplicial homotopy theory. So what is a n-complex? Well, a n-complex is, to begin with, a simplicial set that has the right lifting property. I'm gonna comment in a box in a second what this means in case we don't know. With respect to a bunch of maps, and these maps are usually denoted with this lambda going into delta. I'm gonna say in a second what these are, but the range of the parameters are 0, smaller or equal than k, smaller or equal than m. So let's comment on this definition, since then the big brother n-Complicial set is going to be some kind of variant of it. So first of all, this is a map of simplicial sets, and the domain is what we would call the kth horn. And what is it? Well, maybe I should actually start from this side. This is just the standard M simplex. And the horn is obtained by the standard M simplex by removing the top dimensional simplex and the kth face. So this is the standard simplex without top simplex and kth face. And there is a canonical map that sends the horn into the simplex, and this is the thing that we would refer to as the kth horn inclusion. So this is a map, and this is used to detect when a simplicial set is a n-complex, in which sense. So if I have a simplicial set X, I am requesting that X has the right lifting property with respect to this horn inclusion. So this means that whenever I take a map of simplicial set from the horn to X, I must be able to extend it to a map of simplicial sets from the standard simplex. And we learn in algebraic topology that this is a way to capture that my simplicial set can be regarded as a space where the vertices are the points and one simplices are the edges, and so on. Okay, so let's take this in our bag. And now let's mention a variant of it, which is the definition of a quasi-category. It's going to look pretty much the same. The quasi-category is a simplicial set that has the right lifting property, kind of with respect to the same thing. So the KM horn into the simplex, and the range also looks similar. If I don't pay attention, I may feel like I'm doing exactly the same thing. So let me highlight the difference for you. Now we only allow inner horns. So K cannot be 0 and cannot be M, but before it could be both. Okay, and I'm gonna write it down in a second, but the intuition is that if a n-complex should behave as a space, as an infinity groupoid, as an infinity 0 category, a quasi-category is designed to only select those that should behave as an infinity 1 category instead. Okay. We like simplicial sets very much, and it would be great if we could have a notion of infinity n category that is just based on a simplicial set with some right lifting property. Unfortunately, this doesn't seem to be possible. There's a kind of shift in difficulty when you go from 1 to 2 and higher. And so we need to be a bit more flexible and allow ourselves to work not just with simplicial sets, but with simplicial sets with a marking. Okay, so we are enlarging our ambient a little bit. It's a bit more complicated, but it's not dramatic because a marked simplicial set is pretty much what it sounds like. It's a simplicial set in which certain simplices are declared to be marked. So let's write it down. Marked simplicial set is a simplicial set. Maybe we can say that with the set of simplices that we call marked. And I have a lot of flexibility in this choice. So it's not like I'm expecting a long list of conditions. I only request 2 very mild things. One is that the marked simplices are all in positive dimension. So I cannot mark a 0 simplex. And if I anticipate our intuition a little bit, this makes sense because marked simplices are going to encode invertible morphisms, but it doesn't make sense to talk about an invertible object at this point. And that's why we don't allow marking in dimension 0. And the second condition is that every degenerate simplex should be marked. Once again, this makes sense because in our interpretation that when we have a simplicial set, a K simplex should be a K-dimensional morphism of some kind. When we degenerate it, we're thinking that we're taking some kind of identity on it. So we do expect this to be invertible, hence marked. The first time one sees this definition, you may expect something like, oh, maybe the face of a marked simplex should also be marked. But no, that's not what I want. Because this would be saying something like, if I have an invertible 2 simplex, it means that its one-dimensional boundary is also invertible, but that's not the type of behavior that we would expect. Okay, so we should think that now, instead of talking about simplicial sets as the ambient, the new ambient is a bit larger and it's given by marked simplicial sets. So now, for instance, maps are going to be maps of simplicial sets that preserve the marking. And now, amongst all the marked simplicial sets, we want to select those that we should think of as infinity n categories. And those are the n-Complicial sets of the title. questions?
See, no questions.
Okay. So here's a definition that will not be very useful because there is a lot of notation that you don't know, but I will put it down and then we will spend essentially the remaining of the talk trying to describe the blanks that I'm filling right now. So the definition will look a little bit like the definition of a n-complex and a quasi-category. An n-Complicial set is a marked simplicial set that has the right lifting property. Now, in the world of marked simplicial sets, though, and with respect to not just one family of maps, but 4 families of maps. So the situation is significantly more complex, but we should expect that. We are treating n for arbitrary n. So there is 4 types of maps with respect to which we expect our n-Complicial set to lift. So the first one looks familiar, and it's still some kind of Horn inclusion. It's a Complicial Horn inclusion. I will tell you later what this is, but you can be creative and let your imagination play with it, and you would already get some ideas. So the notation is chosen so that it makes you think that at the level of simplicial sets, this map is really the old Horn inclusion, but now it's in the world of marked simplicial sets. So there's going to be a suitable marking here and a suitable marking here. This marking will depend on K and M. All the other maps are new. And at the level of simplicial sets, all those maps are identities. But in each of these maps, the guy on the right has more marking than the guy on the left. Let's give them some names. So this one is sometimes referred to as the thinness extension. This one is the triviality extension. And the last one is the most complicated one, is the saturation extension. If you have worked with complete single spaces before, the saturation extension is kind of the analog of the completeness condition in this world. Okay, so as I said, I will say more about what each of these maps are, but before going there, let's record kind of a table to keep in mind so that we don't forget our goal. The definition is designed to implement the following intuition. Like for n-complexes and quasi-categories, we expect the 0 simplices to be the objects of our infinity n category. The 1 simplices are the 1 morphisms. And as I already spoiled, the marked 1 simplices should be precisely the 1 isomorphisms. So the marking is meant to tell me, look, this 1 simplex actually has an inverse of some kind. The axioms are designed so that this interpretation will hold. And now, as we go higher with the dimension, subtleties start to arise. I really would like to say that a 2 simplex is the same as a 2 morphism. But it's not quite. And if we draw a picture, we can kind of see it. A 2 simplex looks like this. And if I imagine this being filled by a 2 cell, this is not just a 2 morphism. This is a 2 morphism with a specified decomposition of the target. So it's a bit more information than just a 2 morphism. With specified target decomposition. But if I ask about what is the information carried by the marking, this is the same as one dimension lower. A marked 2 simplex corresponds to a 2 isomorphism with a specified target decomposition. So we would imagine that the 2 cell that is inhabiting these 2 simplex is actually invertible in some sense. And as the dimension grows, the simplicial combinatorics gets more and more complicated. And so all that we can say at this point is that we want to think that a K-simplex is a K-morphism with some boundary decomposition. Gets more and more complicated to grow. But it's worth pointing out that the same K-morphism is represented many times with a different K-simplex depending on how you choose to decompose its boundary. And once again, the marked K-simplices are the K-isomorphisms.
Excuse me, Martina, could I ask a question?
Yep.
The orientation that you've drawn, the 2 simplex there, is not what I'm used to. But in general, I do have to think of these as oriented all the way up, right? As having a particular orientation.
So you're saying you would orient it down?
Yeah, I'm wondering, is the way I should think of these the like streets orientation on these higher simplicities?
I think this is streets orientation. In a sense, it doesn't matter all that much. You would obtain a different definition on the nose of an n-Complicial set if you picked the opposite one, but it would have an equivalent homotopy theory. So in a sense, it doesn't matter. But you have to be consistent. So once you decide which orientation you pick, it's kind of determined in each level how you're filling all the arrows.
Okay, great. Thank you.
Okay, cool.
Can I ask another question at this point?
Mm-hmm.
Could you just briefly say this definition you recalled now, is this the original one due to Verity? Or
yes.
Or has there been some evolution? So, but back then he didn't have the n in there, right? He took n to be infinity, is that right? Implicitly, or not?
So historically, Verity was mostly working only with these 2. So in this sense, the n is not featuring. Actually, I should have stressed this. Once again, if we're talking about an n-Complicial set, where is the n featuring? And the n is only featuring in here. So you're right that in his original definition, he only introduced these 2 maps. But these conditions are not strong enough to capture infinity n. So this one, because clearly if you want to truncate somehow, you need to enforce it. But I think most importantly, in the original formulation that he had, he didn't include saturation. And I think this really leads to more subtle things. Like for sure, for infinity n, without saturation, you are not good. For infinity, there are different routes that you can take and they lead to non-equivalent models. But okay, short answer is in his original series of 2 papers, he only has these 2. But he intended, yeah.
So who introduced the, I mean, 3 is kind of obvious. Who introduced 4, like n-Complicial, whose ideas is really?
It was also Dom, it's just he didn't include it in the literature that he wrote. And then it only appeared in the literature later on. I think Emily wrote down some of it after talking with him. But I think at least the idea, I believe he had it all along. The first time that I've seen it written somewhere, it was in Emily's notes. But I think my understanding is that he was, he had planned all along for it. Yeah, but when you read the literature of Complicial sets, you should always like be careful a little bit about which maps are included, because you know different choices lead to different homotopy theories. Okay.
Thanks.
Okay, so just to clarify, how do we relate the unmarked and the marked context? So we can put the n-complexes here and quasi-category here. And a n-complex is almost the same as a zero-complicial set. And the quasi-category is essentially the same as a one-complicial set, in the sense that the underlying simplicial set of a zero or one complicial set is a n-complex or quasi-category, and there is a canonical marking that you can put on a n-complex and on a quasi-category that makes them into a zero and a one complicial set. So this is really a bijection. And unfortunately, there is no analog that we could put on this first row. And the generalization just lives here, and it's the n-complicial set. And a zero complicial set is used to model an infinity zero category, which is also the same as an infinity groupoid or a space. These are all kind of synonyms. And a one complicial set is an infinity one category. And this is also what people refer to shortly as an infinity category. And then an n-complicial set is then an infinity n category for general n. Okay. So I'm going to tell you a bit more about the maps. So I promised to you that the request is that my n-complicial set should lift against 4 types of maps. And I'm not going to give you the full definition of all of them. I'm going to give you the baby instance of each of the 4. So let's start with the first one. The first one was the complicial horn. There are 2 parameters, and the first interesting instance of it is when k is 1 and m is 2. So in this case, we are staring at lambda 1, 2 and delta 1, 2. So what are they? Lambda 1, 2 as a simplicial set is just the usual horn that we would draw as kind of 2 consecutive one morphisms. But now it's a marked simplicial set. So I also need to tell you which simplices are marked. And in this case, I would like to say that nothing is marked. This is slightly wrong because I said that all the generate simplices have to be marked. But other than that, no interesting simplex is marked. And on the right box, I have the 2 simplex as a simplicial set. But now something is marked, the 2 simplex. So I'm decorating it with this kind of red equivalence. So what I'm displaying here is not a map of simplicial sets, it's a map of marked simplicial sets. And if we think about it, what does it mean to lift against this canonical map? It means whenever I select 2 consecutive one simplices in my n-complicial set, not only must I be able to fill a 2 simplex in there, but this 2 simplex has to be marked. And we like this because since the 2 simplex is marked, it means that this triangle is inhabited by an invertible 2 morphisms. So we're kind of entitled to think that the new one simplex is the composite of the other 2, which we would have not been allowed to do if the simplex had not been marked. So the punchline about the meaning of lifting against the map of type 1 is that it encodes the fact that you can compose morphisms. So since I only showed one instance, this one instance is only telling you that you can compose one morphisms. But if you allow different values of k and m, this is going to encode that you can also compose 2, 3, 4, 5 morphisms and so on. This is good. Cool. Okay, so let's move on to the second one, which is maybe a bit new because, as I said, now maps of types 2, 3, and 4 are all identities at the level of simplicial sets. It's just I get more marking. So I'm still focusing on the smallest interesting value, which is k equals 1 and m equals 2. What do they look like? So now we are staring at something denoted delta 1, 2 prime and delta 1, 2 double prime. Notation is not great, but that's what it is. So both these marked simplicial sets are the two simplex that I redraw for you. But the marking is different. In the domain, I mark, I believe, this one simplex, and the two simplex. In the codomain, I mark, well, at least the same ones, because otherwise I wouldn't have a map. But I'm also marking more, and I'm marking the last one simplex. So let's think about what it means for a simplicial set to lift against this map. It means whenever I take a marked two simplex, this already means by point 1 that the bottom leg is to be thought as the composite of the top two legs. I am also requesting that the 0 and the 2 face are marked. And the existence of a lift with respect to this is just saying then the bottom has to be marked too. And I can try to rephrase it, but this is the type of thing where you would see it best if you just sit down and try to write down what it means. But in practice, this says, if I'm trying to compose two morphisms that are marked, the designed composite also has to be marked. So maybe we record this as composite of iso is iso. And once again, the specific case that I'm drawing only looks at composition of one-dimensional morphisms, but for different values of k and m, you would make sense of an analog statement for higher dimensional morphisms. Okay, the triviality map is kind of easy overall. Essentially, it's designed to encode the fact that every simplex, every morphism in dimension higher than n should be marked. All iso in dimension bigger than n. So how do I encode these in terms of a right lifting property? Well, I would say that it has to lift again this map, where this is the kind of unmarked M simplex. And this is the M simplex with the top simplex marked. So for instance, the one that we're seeing over here would be delta 2 thin, delta 2t. And this part would be delta 1t. Now, lifting against this map means every time you pick a simplex that has dimension bigger than n, it has to be marked. And so this map is precisely making sure that we're designing an infinity n category, like it's capturing the critical level after which everything should be invertible. Okay. And the last one is the saturation extension. I'm gonna write down what the kind of lowest dimensional case looks like. And this would be delta 3 ec and delta 3 sharp. So let me describe a little bit what are these two marked simplicial sets. So both of them as simplicial sets, they're just an ordinary 3 simplex, but the one on the right has more marking. So I drew my, is there a question?
Sorry, Martina, if you can lift up the page a little bit because it's truncated on the screen. Yeah, here you go. Thank you.
Cool. So I drew the 3 simplex flat over here. So you see I have the 4 vertices. Oops. And they are reproduced twice, just because it's easier to draw it flat rather than not. And in, I guess, purple, I indicated which simplices are marked. So the 3 simplex itself is marked. All the interesting 2 simplices are marked, these 4. And 2 of the one-dimensional simplices are marked, the diagonal ones. So this is what delta 3H is. It can look weird, but it has a very intuitive meaning that I will comment on in a second. And instead, the one on the right is marked fully. So every simplex that you see is marked. I have a map of marked simplicial sets. And now if we think about what this means, this is kind of saying, so maybe I'm gonna give some names. So what does it mean to map delta 3H into some marked simplicial sets? It means I'm picking some F, some G, and some H. And since this simplex is marked, whatever is on the diagonal is to be read as a composite of F and G. And since this simplex is marked, whatever is in the diagonal is to be read as a composite of H and F. And so if we like spell out completely what this amounts to, we are essentially saying that we are picking F with an inverse on one side and an inverse on the other side. And the request is that at this point, then F itself should be marked. You know, if it's the first time that you hear this, maybe it takes a little bit of time to digest, but I invite you to sit down if you're interested after the talk, try to write down for yourself what this means, and you will realize that lifting against this map means that if a morphism has left and right inverse, it is an iso. This may look like a tautology, but it's not at all, because so far, what we were calling the isomorphisms were picking completely arbitrarily. You know, I could take a simplicial set, add some marking in a completely stupid way. So if I pick a marking in a totally stupid way, it's not going to reflect my intuition that marked should amount to invertible, to isomorphism. So this axiom is crucial in capturing this. And once again, I only discussed the kind of the lowest case, but the higher values of L take into account a similar situation for morphisms of dimension higher than 1. Okay, so to recap, we kind of accomplished what we promised. We decided what the intuition was supposed to be. We decided that a K-morphism was supposed to correspond to, a K-simplex corresponds to a K-morphism with some boundary decomposition, and that the marking should encode invertibility, and the 4 right lifting properties encode what we expect. So we see that we can compose stuff, that composite of invertible things is invertible, that everything is invertible in dimension higher than n, and that isomorphism really means invertible, and it's not just some like artificial, nonsensical definition. Okay, so this is pretty much the definition, and I was just going to end trying to mention some of the advantages and disadvantages of this model, because as I said, I don't believe that there is a perfect one. It just works well for certain things and bad for others. So here are some very short lists of things that I think work well or don't work well with this model. So amongst the good ones, there is the fact that n is a fixed parameter, but somehow the difficulty doesn't really grow with n. So once you have digested the definition, discussing an infinity 2 category or an infinity 500 category more or less amounts to comparable difficulty. It's the same type of underlying object, and I just have to be careful with the role played by the parameter in the lifting properties. Instead, with other models, say if you're working with, I don't know, n-fold complete single spaces, if you want to construct an infinity 500 category, it means you're dealing with something indexed over 500 copies of delta, which might cause complications depending on how explicit you want to be with your formulas. Another advantage is that this model is really the closest in many ways to quasi-categories and complexes. The literature is very developed. Even for quasi-categories, we have all the Joyal and Lurie have written, and you can kind of upgrade a lot of the arguments to the marked case and make them work for infinity n rather than infinity 1 or infinity 0. And the last one is that it's very easy to say what a map of infinity n categories is in this model. It's just a simplicial map preserving the marking, period. So everyone could write it down. Instead, if you're working with maybe some categories strictly enriched over a model of infinity n minus 1 categories, you would have to cofibrantly replace the domain to make sure that you're capturing all the maps, and this is a pain. Okay, and there's more. This list is not supposed to be exhaustive. What are some of the negative sides? I personally find that one of the negative sides is that morphisms are overly represented. So as I was saying earlier, if I start even with a strict 2 category that I like, the same 2 morphism in this 2 category will correspond to many simplices. And in fact, you can see this even with the toy example. I have a paper with Victoria Ozornova where we prove that if you look at the nerve of the walking 2 morphism, so you take just a 2 category that has a single interesting 2 cell and that's it. And then you look at the nerve of it, you would expect it to have only finitely many non-degenerate simplices because everything is very finite, you can't compose anything. But no, it has infinitely many non-degenerate things. So there's this over-representation that does not contradict anything at the level of homotopy theory, but at the point set level, things are just very big. There's too many representatives of the same thing. And another thing is that composition is mysterious. You can still manage when you're trying to compose one-dimensional morphisms because the horn is kind of nice. But when you're trying to compose morphisms of a higher dimension, you first need to kind of rearrange the boundary in a way that it fits a horn. And it's particularly complicated. So it's not immediate how to compose 2 4 morphisms if you're given 2 such things. Okay, I think I'm on time to stop and I can take questions. Thanks.
Great, thank you very much. Any further questions?
Yeah, thanks for the very nice talk. I have a question on this. This one advantage or disadvantage you mentioned of the n-fold complete single space, where you say, okay, if we're working with 500 categories, then we have these 500 copies of delta. That's of course true. On the other hand, it was this feature, wasn't it, of n-fold complete single spaces that really allowed Lurie in his article on conformal field theories, on classification of topological field theories to make progress, because it so happens that actually describing n-Bourdisms is easy in this n-fold way because you effectively draw them inside a big cube and regard that cube as being parametrized on all its edges by simplices. So somehow that was actually a way towards progress. So I'm wondering, how easy is it actually to now encode cobordisms in this completion language? The kind of the intrinsic geometry of cobordisms is very non-simplicial in a sense, right? So you have to
Yep.
kind of force it into this picture, right?
So I would say that there's generally like two types of questions that one may want to address, and sometimes it's working hands-on on a specific infinity n category, and this will be the situation maybe of like building infinity n category of cobordisms, or more like developing the theory. And I think I've mostly worked in developing the theory, but I am interested in trying and understand some of these like infinity n categories that people work with and encode them in this model. And I think that Verity actually had some ideas on how to build a completion set of cobordisms. So I think that there were at least some ideas. But it's what I was saying, I really feel like in this subject, everything is at the same time an asset and a flaw. Like it's really like depending on how you look at it. So yeah, I think n-fold complete single spaces are particularly good because it's easier to iterate stuff somehow. Like you can always add an extra dimension inductively, kind of, which you will not be able to do in this model. So I think this relates a little bit with what you're saying, that it's exploited a lot in every construction related to like the cobordism hypothesis, that n-fold complete single spaces have a very inductive nature. Yeah, I'm not sure if this like addressed your question, but here are some thoughts on it.
Yeah, thanks for that. Maybe I can briefly follow up. Do we have good comparison functors from n-fold completion sets to say n-fold? Sorry, I should say n-completion sets to n-fold single spaces or backwards, or?
I think so. There is a big chain. Like all the models that I mentioned are known to be equivalent now, but you don't have direct comparisons between any two of them. And in particular, I don't think that there is a direct one between n-fold complete single spaces and n-completion sets. There is one, so you could go direct between n-completion and theta n models, and then I think theta n models are compared directly with n-fold complete single spaces. And many of the comparisons are done in the language of model categories and Quillen equivalencies. So sometimes, even though the comparison is not direct, you can still manage to work with the zigzag.
Right, thanks.
Any other questions?
Martina, how much has been done on the sort of category theory of n-completion sets? Like, well, I find myself needing to co-complete tri-categories under Classley objects. Is that something that I could do if I worked instead with 3 completion sets?
So are you asking about a theory of limits and colimits in n-completion sets?
Yeah, Yoneda theory, limits and colimits, stuff, the stuff like that.
So for n equals 2, Lurie's infinity by categories are similar to 2 completion sets. And like Gagné-Harpas-Lanari have something specific for n equals 2 for certain limits or colimits. But I'm working with Lin and Nima, not in n-completion sets. We're working in other models, develop a theory of limits. And we are hoping that the approach that we take there eventually will be pushable also to n-completion sets, but it will be a further step. So right now, I'm not sure of how much it has been done in terms of limits and colimits, but you should have a look at Gagné-Harpas-Lanari for n equals 2, but you said you are doing 3, right?
Yeah, 3.
Okay, yeah. I don't know. Wait until our stuff with Lin and Nima comes out, and maybe then we can push it also to this.
Thank you.
Any other questions? Okay. No.
Right. So allow me maybe one question on this point. So I understand everything is difficult, but now beyond this definition, could you just indicate what has been done with the theory? Like what can be,
Mm-hmm.
right? What's
Let me
the
see.
use case?
So I wrote here some stuff that Victoria and I have worked with in different combinations, and Victoria Ozornova, and also with other people. So again, this is not supposed to be a complete list of the like kind of literature of complicial sets, just some things that we've worked on. So one thing that we did with Victoria is that we constructed an embedding of the homotopy theory of strict 2 categories into the one of infinity 2 categories. And we were able to prove that this was really an embedding. So this is a kind of a solid sanity check that whichever theory you are building for infinity 2 categories kind of extends appropriately the strict theory. And what we do really is for n equals 2, but some of the argument could extend also for general n. With Andrea Gagna, we discussed some degree of compatibility of the join construction and the nerve embedding. So there is a join construction that you can do on strict omega categories, and there's a join construction that you can do in complicial sets. And in a sense, this join is compatible with the nerve embedding. So here you really see where the nature of n-Complicial sets is good, because they are kind of designed to host a join construction, which is much more complicated in models that rely on different shapes. But you know, when you work with simplicial stuff, the join is kind of built in. And the last thing that I'm mentioning is with Dominic Verity. So he, to begin with, had kind of a proposed model of the gray tensor product before saturation, and he had already proved that it had good homotopical properties before adding saturation. And then together with him and with Victoria, we actually did also the verification that the gray tensor product is well behaved with the homotopy theory for infinity n categories. I believe that this is one of the few models where the gray tensor product for general n is made explicit. But if not, it's one of the few. Yeah. So these are like some directions of like developments that were done using this model, I would say.
Very good. Any other questions? If not, let's thank Martina again for the very nice talk.
Thank you.